All right, good morning. Here we are again for another lovely session of MENG 3310 Fluid Mechanics. This is going to be the 22nd lecture in the video series, and this is going to cover an introduction to dimensional analysis, similitude, and other areas of experimental design. So, for this portion of the lecture, I have a few learning objectives. First, I wish to, I wish to describe the needs and benefits of similitude in fluid mechanics. I wish to define what a non-dimensional parameter is. Third, I wish to describe common variables and dimensionless groups used for creating models. And fourth, I wish to apply the process of repeating variables to determine pi terms. So let us begin. So first we need to talk about unit systems, dimension systems, etc. So we know that we can define units many different ways. We can define units in terms of, we can define specific units. Like we can define a slug, we can define a kilogram, we can define a newton, we can define a pound. Those are units. But I want to get to something deeper. And so units are arbitrary. Units are completely arbitrary. They can be anything. What is not arbitrary is dimensions. So let's talk about dimensional systems. So when I say a dimension, I am talking about a type of measurement. In other words, I can define a unit. If I have a unit of weight, I can make that whatever I want. I can make it a pound. I can make it a newton. We can define weight, a unit of weight, as anything that we find convenient. And so nowadays in modern unit systems, we use in the modern metric system, and we use you can actually look up the definition of a meter, and it's related to something about, or you can look up the definition of a second, and there's a very precise scientific definition that talks about something like the pulsations of cesium atoms and suspended in a laser field or something really exotic like that. And we use these definitions we try to create unit systems we try to create units that are very precisely defined, that can be verified independently in lab settings, that kind of thing. Well, but the actual units themselves are completely arbitrary. These are human creations. So units are arbitrary. Dimensions are not. Dimensions are not. So when I say dimensions, I want to talk about two systems, and I'm going to talk about first the MLT system, MLT, and then the FLT. These are our two main ones, although we could define dimension systems really using anything. And these are, the MLT is mass, length, and time. And FLT is force, length, and time. We can define, when we define our unit systems, we define what we consider fundamental quantities, fundamental dimensions, or fundamental units. So, for example, in the metric system, we consider if we're using an MLT system like the standard metric system, we are saying that a kilogram is a fundamental unit. We're saying that a meter is a fundamental length. We are saying that seconds are a fundamental unit of time. So we're declaring our fundamental units. So for example, we say MLT would be a kilogram, a meter, and a second. And then everything else is built off of these. So we can say, 1 newton is 1 kilogram meter per second squared, right? We can say that a newton is a kilogram meter per second squared, or we can define a joule, right? And this is built off F equals ma. We can say that 1 joule equals, for example, 1 newton meter, or a kilogram meter squared per second squared. And so look at this. We are saying that a joule is not a fundamental unit. We are defining a kilogram as a fundamental unit, a meter as a fundamental unit, and a second as a fundamental unit. And then we are defining a joule, a unit of energy, based upon what we consider our fundamental units of mass, length, and time. This does not need to be the case. We could actually define energy as our fundamental unit and then build definitions of length off of that. Or we can define, we could pick anything we wanted to. we could say that we could define a unit for momentum, a unit for energy, and a unit for maybe something else. I'd have to do the math to figure out what the third one would be, and then just build everything else off of that. And so there would be no, like, for example, when I say a mass is 1 kilogram, yes, I can say that that's equal to, say, a kilogram is equal to a Newton times second squared divided by a meter, but I can't break a kilogram into anything more fundamental. There is nothing more fundamental than simply mass. It is a fundamental unit in our unit system. And so, but we could define energy as something as fundamental, et cetera, et cetera. But, so we need to distinguish between dimensions and units. Units are just the size of a dimension. So that's the difference, I should say. A unit is just a quantity, or a quantity, measurement, or size of a dimension. Measurement or size of a dimension. So, units are arbitrary. Units are arbitrary and dimensions are not. Dimensions are fundamental. If I can squeeze this in here, fundamental. So again, what I mean by this is that if I want to measure the dimensions of this room, for example, I am going to need 3 dimensions. I'm going to need 3 length dimensions. I'm going to need something in the length, width, height, that kind of thing. That's fundamental. I can define length however I want. I can use meters, I can use centimeters, I can use feet, I can use cubits if I want to. I can be really weird and define what I call a Larson, and just define some really weird unit called a Larson that just means something particular to me or something like that. I could define if I was measuring something in if I wanted to replace the kilometer or a unit of that size approximately, I could define the Larson as the exact distance from my front door to the front door of the campus, and just do all my calculation in Larsons if I wanted to. I probably wouldn't get much. If I started publishing papers using unit in Larsons, well, I probably wouldn't get those published very often, and people would think I was quite conceited. But theoretically, there's no reason I couldn't do that. At least, it would still be, I could publish something, or I could write a paper or something like that using really weird units. Like, I could define a unit, or actually, I could have really fun with this. I could define 3 different units. I could define my own custom weight, height, and time units. I could define the unit of weight I could literally step on a scale and measure my weight and define that as 1 Larson unit of weight. Oh, we could make that like pounds mass and pounds force. We could have Larson measurements of mass, which is my mass at the time. I just find some particular, actually I'll measure my mass over a period of a month and average those together, so to average it out. So that will be the measurement that will be Larson mass. And then I'll measure my own height, and we'll define that as Larson length, and time, my age or something like that, and divide by some constant or something like that. And I could define my own crazy custom unit system. I'll have Larson mass, Larson length, and Larson time, and there's my MLT system, and I can just define everything all off of that. We can have Larson momentum, we can have Larson energy, we can have Larson angular momentum. We can do all of this stuff. We can build all the physics off of my own ridiculous unit system if I wanted to. Now, again, people would think me rightfully crazy if I actually went through and wrote a textbook in Larson's, but there is no reason I couldn't do so. So that is the difference between a dimension and a unit system. So although I've joked before that it would be, maybe I'll do that if I'm ever a really ancient tenured professor somewhere. If I can't be fired, I'll just put together a class and just define my own crazy unit system and teach everything in that crazy unit system and just drive everyone crazy. But anyway, and that's why I'll never get tenure. Anyway. Okay. Anyway, so let's work with some examples with dimensions. So let me look at a few more examples with dimensions. So let's say I want to verify the Reynolds number. That's something we'll see. The Reynolds number is the most common, what we call a dimensionless term. I want to verify the Reynolds, and the Reynolds number is defined as density times velocity times diameter, this is diameter d, over viscosity mu. So I want to verify this, verify that Reynolds number is dimensionless. And this is one of the most common dimensionless parameters that we use, so that's why I want to work through this. So I'm going to do this once in FLT and one in MLT. So let me do it in MLT, and then in FLT. And again, FLT means force, length, time, not faster than light, which is impossible as far as we know. And then, so I'm going to go through these. Now, I'm going to use a particular notation here. And notice I'm going to have not an equal sign, but an equal sign with a dot over it. And what this means is that this quantity has units of. So density has units of mass times length to the negative 3. Velocity has units of length times the negative 1. Diameter has units of length, and viscosity has units of mass, length to the negative 1 times the negative 1. Then here, if I want to use FLT, well, density, instead of having units of ml to negative 3, it's going to be a bit more complicated because now mass is not one of my defining dimensions. So now density would have units of, I basically need to convert my force to a mass. So if you work through it, you'll find that density would have units of F, L to negative 4, T squared, T squared. And here, velocity would have units of L, T to the negative 1. Density would have units of length, and viscosity would have units of F, L to the negative 2 times time. And the Reynolds number would have units of, so actually then we work through the Reynolds number for each of these. So let me just take, what I'm going to do is I'm just, in this expression here, I'm just going to replace each term with its dimensions. And so if I replace density with density here, et cetera, I will get ml to the negative 3 times L T to the negative 1 times L divided by ml to the negative 1, L to the negative 1, T to the negative 1. And let's see, let's start canceling out terms. Well, first the mass will cancel out. And then I have times to the negative 1 and times to the negative 1. And I have a length, and this will, so if I multiply, if I add 1 plus negative 3, I get L to the negative 1, and then I just have L to the negative 1. So those cancel out. So what I end up with, very simply, is that the Reynolds number is equal to m to the 0, L to the 0, and times t to the 0. So, in other words, this is a dimensionless number. Now, this does not mean that the Reynolds number itself has no number. It does have a number. It can have a value based on, like, we can actually calculate the Reynolds number for a given fluid flow. Like, if you have a fluid that's going through a pipe of a certain diameter with a certain viscosity, a certain density, etc., you can calculate the Reynolds number, but that number is dimensionless. And as we'll see later on, it being dimensionless gives it certain abilities and certain properties that are special, and we shall see that. So I could do the same thing for the Reynolds number for the FLT system. And if something is dimensionless in one dimension system, it will be dimensionless in the other dimension system. It does not matter whether you're looking at it from the point of view of an FLT system or an MLT system. No matter what, it will be dimensionless if you do it right, which doesn't always happen, but such is life, I suppose. L to negative 4 t squared times L t to the negative 1 times L for diameter divided by F L to negative 2t, and if you work through that, you will find that it has units of simply F to the 0, L to the 0, t to the 0. It is dimensionless. And again, this is important for what we'll learn later, which is dimensional analysis. All right, so let me now define dimensional analysis, or start looking at this. So dimensional analysis. Dimensional analysis. So let us say that let us consider a smooth-walled horizontal pipe. A smooth-walled horizontal pipe. So let's say we have a certain pipe here. Let me draw a crudely rendered pipe. So we have a certain pipe here with a certain diameter, etc. And this is going to have a certain diameter d. And then let's say it has so it's going to have a diameter d. It's going to have, inside it, there's going to be a fluid velocity v. And then there will be a viscosity mu and a density rho. So the fluid then will have properties of density mu and, viscosity mu and density rho. So let us consider this. Now, we want to determine the pressure drop per unit length. The pressure drop per unit length in other words, the delta PL. The delta PL. And so the question is, what units do we use? So what units do we use? So I'm interested in, if I want to look at this, if I want to design a setup, well, I know it has to be a function of certain things. So I know it has to be some sort of function. In other words, if I'm trying to determine a setup or an experiment, to determine what kind of things affect pressure drop, well, first I take a list of all of the things that might have an effect on it. Well, so even with some very rudimentary knowledge, well, the kinds of things that might affect it are the velocity, the density, the viscosity, and the density. Does that make sense? I mean, those are really the only things that might have some sort of effect on the fluid flow. Now, we could also talk about temperature, that kind of thing, but we could probably surmise that those would be worth experimental analysis. But we might surmise that temperature would have an effect only because it's affecting viscosity and density, etc. So these might be the main variables that will affect the flow. So let's say I want to look at how these variables affect, let's say I actually tasked you with determining, okay, we have this new type of pipe, I've invented a new type of pipe made from a new material, and I want to task you with determining, okay, develop some sets of equations that will predict how, now, we have seen that in idealized systems we can calculate, the pressures and velocities of fluids and et cetera, using simple energy methods. But in real life, in the real world, in the non-perfect world, there's always energy losses. And so let us say I want to determine experimentally how these actually work. Well, let's think about this. Look at this system. I have 5 variables. I have 5 variables. I have 4 independent variables and 1 dependent variable. What I'm interested in is the delta PL. I have 4 independent variables. Can you imagine designing an experimental system to investigate 4 independent variables? Can you think about that? Can you imagine how difficult that would be? Think about that. How difficult would it be to create a system like that, to create an experimental regime like that? Because you can't just change one of them. You can keep one constant, or you can keep 3 constant and vary the others. But then, how do you know your results will be the same if those 3 weren't constant? How do you develop the relationships therein? This gets very difficult. This gets very difficult indeed. So trying to develop an experimental regime where you have 4 independent variables, you're going to be doing tens of thousands of independent experiments, maybe even hundreds of thousands or millions. I mean, the number of experiments increases to like the power of n kind of thing. This is literally exponential. So you just have to start considering all the combinatorics, all the combinations therein. This is very difficult. So this is an experimental nightmare. To try to do this experimentally is a nightmare. So we need to find a better way. In other words, we need to develop a new set of variables. A new set of variables. That will reduce the complexity of the system. So we need a new set of variables that will reduce the complexity of the system, or of our experimental regime. Okay. Let's see. So let's define what we mean exactly by dimensional analysis. So let's define dimensional analysis. Well, I would define dimensional analysis as thus. I would say that dimensional analysis is a method to combine variables into fundamental dimensionless terms. Variables into fundamental dimensionless terms. Dimensionless terms. Example, the Reynolds number that we saw previously. So remember the Reynolds number? We saw previously that its dimensions come to 0, or come to 1, I should say. So the overall, it's dimensionless. If you work through the fundamental units and divide them out, you will find that the Reynolds number is a dimensionless quantity. So, and actually Reynolds number is the most important dimensionless quantity in fluid mechanics. It's one that pops up again and again. So Reynolds number is most important dimensionless quantity, but we'll need to learn how to develop our own and others as well. But Reynolds number is one that pops up again and again in fluid mechanics, and we'll see some more again today. So again, the whole purpose of this will be that it simplifies functions and experiments. It will simplify functions and experiments. So again, for example, the previous system, what if there was a way to work with only 2 variables? That's what I would like to do. That would be the very ideal system. So remember the previous system where we had all of those 5 variables, 4 independent variables, 1 dependent variable? What if I had only 1 independent variable? Suddenly that would be very easy to experimentally work with. I could just have one system, I perform one experiment, I set up one curve. That would be very easy. So let me go back here, sorry. For example, I want to create what I call dimensionless products or groups. I want to create dimensionless products or groups. So for example, we will see that in the previous problem, you can actually do something like this. You could define something kind of like this. If we did this kind of thing, d delta PL over rho v squared equals, and I'll use the variable phi here to refer to a function of rho vd over mu. And I need to introduce what I call a pi term. This whole quotient here is a pi term, and this whole quotient here is a pi term. And phi is just going to mean some function of. So we develop some sort of pi term, and we'll have one pi term and another pi term, and then we'll perform some sort of experiment where we do this kind of thing, where we plot one pi term on one axis and another pi term on another axis, and we get some feel for the behavior of the system. So instead of plotting, say, just the density, maybe my independent variable will be density, velocity, diameter over viscosity. And on this one, I'll have d delta PL over rho v squared. And then I'll have some sort of function connecting the two. And so this would be a very easy experiment to determine. All I would have to do is just choose any pipe size and fluid that's easy to work with. I could do the same experiment with air or water or oil or hydraulic fluid or anything that I wanted to, and it would still work out. So this can be very useful. And creating these pi terms is not necessarily the easiest thing in the world. In fact, we're going to have to learn we'll have to explore something that we call Buckingham Pi theory, and that's what we'll be working on now. So let us discuss Buckingham Pi theory. Let's discuss the Buckingham Pi theorem. So what this is a methodical way to derive meaningful dimensionless terms. So we could just bang our head against the wall and do this through trial and error, but we would like to have a method to do this. So if you actually start playing with these, you can find that it's kind of difficult to actually come up with these. It looks very easy when I just write them on the page and say, oh, here's a pi term. Very simple, but we need something more, we need a guided process in order to actually find these things. So I want something a little bit more methodical. It's a methodical way to derive meaningful dimensionless terms. Meaningful dimensionless numbers, which again we are calling dimensionless numbers pi terms, which are pi terms. And the first step will be to determine, it will determine, it also determines the number of pi terms needed to describe a system of pi terms, or the quantity of them, pi, py, rho, pi terms needed to describe a system Now, if I were really clever at this point, I would display on the screen a graphic of a young boy on a raft with a tiger or something like that, but we'll have to avoid that this time. Anyway, so the general rule is shopping list. Someone updated my shopping list. Let's get rid of that. Sorry. Okay, interesting. So the rule here, how do you determine how many pi terms you need? Well, k variables can be reduced to k minus r pi terms. This is our guiding relationship here. k minus r pi terms. And I need to actually define what r is. So again, k is the number of variables. In other words, like in the previous example, a variable was diameter, a variable was pressure drop, a variable was density, a variable was viscosity, etc. Number of variables. And r is the minimum number of reference dimensions required. The minimum number of reference dimensions required. Required to describe the variables. To describe the variables. So, in other words, if you had a system where everything was in units of length, well, your number of reference dimensions would just be r. You'd only have r. But in this case, if you have L, T, and M, well, that means that r is equal to 3. So you need to look at what is present, and then look at, you got to look at the variables you have, and look at how many dimensions you need to describe them. If you need so the maximum r can ever be is 3. So max r is 3. R can be either 3, 2, or 1, or I suppose 0 if you had all dimensionless terms. But in this case, we can see that a larger r value actually helps us. A large r value actually helps us because that allows you to reduce the number of pi terms. That allows you to reduce the number of pi terms. So if you have only one dimension, well, that means you can only reduce your number of variables by 1. If you have 3, you can, if you have 5 variables and 3 dimensions, you can collapse that to just 2 pi terms. And that makes things, and so the fewer terms, the better, because that means you can have a more simplified system. So again, let's go back to this. For delta p as a function of L is equal to a function of or delta p per unit length, the pressure drop per unit length, is a function, some sort of function of diameter, density, viscosity, and velocity. Well, let us look at this. So again, diameter has units of length, rho has units of ml to negative 3, so this is the kind of analysis you need to do. Viscosity has units of mass, length to the negative 1 times the negative 1. Velocity has units of Lt to the negative 1. And delta PL has units of mL to the negative 4, T to the negative 2, L to the negative 1. Or this could then collapse to simply here something like, oh sorry, this is negative 1 here, sorry. This could collapse to mL to the negative 2 times the negative 2. And this again is in the FLT system, or sorry, the MLT system. Or I could say that in the FLT, density has units, or sorry, diameter has units of length, density has units of F, L to the negative 4, T to the negative 2. Velocity has units of L, T to the negative 1. Viscosity has units of F, L to the negative 2, T. And pressure drop per unit length has units of F, L to the negative 2, L to the negative 1, or also units of F, L to the negative 3. And again, this is for the FLT system. The FLT system.
I think you put an L, yeah.
Oh, sorry, that's a typo there. That's an F. Okay. And notice, let's look at this here. So, let's try to interpret this. Well, I'll get this now. You will note that you will get the same number of pi terms, the same required number of pi terms, whether we look at one or the other. So first let us consider the k. Well, in this case, k is equal to 5. The number of variables. K is equal to 5, the number of variables. And then, let's see, r. Well, r is going to be equal to 3. R is going to be equal to 3. Well, the reason I know that is because, well, look, I got mass, length, and time in here, so I'm using every dimension at least once. So this is the number of reference dimensions. Number of reference dimensions. And then the number of pi terms is going to collapse to 2. We're going to come to 2, so we can collapse everything to 2 pi terms. Is going to be k minus r, which is equal to 2. And so I'm going to have a pi 1 and a pi 2. And so pi 1 is going to be some sort of function of pi 2. Now, it's important to note that our Buckingham Pi theory will not give us this function. That we can determine suitable pi terms simply from just calculations like this, simple workings with, we can determine those just by working with the units. But the actual function, that can only be determined experimentally. We're going to have to do an experiment, we're going to have to collect some data. I mean, this function can be anything. It can be linear, it can be quadratic, it can be it can be a logarithmic, it can be exponential. Any kind of function there is, you could have a relationship. So this does not tell you the relationship, but it makes it much easier to build an experiment to determine the relationship. Again, if we have 4 independent variables and 1 dependent variable, 5 variables, that is experimentally unsolvable. There is no way that you're going to be able to create an experimental regime complex enough to really tease out all of the variables. So you have 4 degrees of freedom there, 4 independent variables. That's going to take millions of experiments because again, the number of experiments required, the number of trials, basically, it increases to the power, or maybe even maybe even more, maybe even faster than the power of the number of variables you have. So I would say basically again, what this is all based on is something like I don't know if this is exactly how it would work, but the number of trials needed in an experiment, I would guess it would be something like some constant to the n power, where n is the number of independent variables. I would guess that at least. And this is the reason fundamentally why we learn how to use pi terms. So I don't know if this is exactly how it would work, and actually there'd probably be some other constant in here. Maybe there would be another, maybe I could say it's proportional to this, something like that. So in other words, if I have 1, I have n equals 1, maybe I only need 10 trials, or maybe only 20 trials or something. So maybe I would do something like, I could just create a series of data points. I would just have my independent and my dependent. I measure it, and I get a series of points, and then I use Excel or some other mathematical tool to find an approximate best fit function for those independent and dependent relationships. But if I have if I have 4 independent variables, I might need to do 20 to the 4th power of experiments. And what does that come to? Let's see. I might throw that in a calculator right here. I could do that, I suppose. Well, let's see. Times 20. Look at this. Looks at this, really. That would be something like 160,000 independent experiments. In other words, even if I have all the funding and time in the world, I will not be able to do that. There is no way that I will be able to tease out the relationship between all these variables until long after I am dead. Even if I can do 1 a minute or something like that, or 1 an hour, something really crazy like that, there is no way I can do this. It's simply not possible. etc. So we need to use things, even if we had all the time and patience in the world, there's no reason or no way we can do this. So let us talk in detail about how we actually get these pi terms. Let us look directly at determination of pi terms. Well, actually, I may save that for the next video. I think this is a logical breaking off point here. So that will be continued in the next portion of the lecture, which I think we're actually going to record today, but I'll stop there.